Welcome to Math Explore Infinity. Today we are going to explore another fascinating concept, notably the dual space of a Hilbert space. But fear not, I'm going to try my best, right, to make it as clear and straightforward as having supportive classmates right by your side. So let's dive right in. Imagine our Hilbert space as a math classroom filled with rows of desks, each representing a different mathematical concept or idea. Now, think of the dual space as having some amazing classmates in that classroom with you. I mean, the good thing is that they are not just any classmates, right? I mean, they are super helpful ones. Their special talent is to simplify complex math concepts and make them easy to understand. I mean, they are like those classmates you wish you had in school. Well, now let's say your lecturer or teacher explains a challenging topic, but you are not quite grasping it. That is actually where your helpful classmates from the dual space come in. They will sit right next to you and say, hey, let's break this down together. They will use simple, straightforward explanations, just like having a study buddy, right, who makes things crystal clear for you. I mean, you can think of this channel, for instance. Now, why is all of this important? Well, just like having helpful classmates can make math class a breeze, the dual space helps us understand mathematical spaces better. It's actually a powerful tool used in various domains, I mean quantum mechanics, signal processing, optimization, and so on. So um, I strongly invite you to become that helpful classmate by joining our mathematical classroom, which is the dual space of a Hilbert space for today. And if you're still not sure whether you should subscribe or not, well, let me tell you something that might sound funny. I mean, think of not subscribing to this channel as being like someone lost in the desert, unaware that they have a life-saving bottle of water in their bag. So don't let valuable knowledge slip through your grasp. Dive into discussions, ask questions, and share your own insight in the comment below. Together, we can actually, I believe, we can make mathematics as simple and enjoyable as studying with friends, ensuring that no one is left thirsty for knowledge in this vast mathematical landscape. Well, I'm pretty sure I mean, you wouldn't want to be that person in the desert, right? Thirsty and unaware of the precious resource within reach. So if you haven't already, be sure to subscribe so you never miss out on our exciting mathematical explorations. I mean, subscribing is like always having your life-saving bottles when it is needed most. I mean, when you're feeling thirsty for knowledge, it's like having that essential compass, right, guiding you through the desert of mathematics, ensuring that you will always have access to the refreshing well of mathematical insights. So I think this was a bit of too much talking. So let's dive into the mathematics per se. So we start with a theorem. So in continuation with the previous lecture, so this is theorem 5.5. Looks a bit ugly, but I think that's okay. So this is the Riesz-Fréchet Representation Theorem. So Riesz, oops, Fréchet Representation Theorem. So what does it say? So given phi, right, be an element of a linear bounded operator on H, right? I mean, H is actually a Hilbert space here, right? So given phi, linear bounded operator on H, there exists, let me put it in color, there exists a unique unique f in H, right, such that phi u, I mean this dual pairing, this is just another way of saying phi of u, right, such that this is equal to the scalar product of f and u. I mean, remember we denoted the scalar product by those brackets. And this should hold for every h in u. Moreover, we even have that the norm of f, right, is exactly the operator norm of phi. So let's go into the proof, right? There are multiple ways, I mean, there are multiple ways to approach this, approach the proof, right? But I mean, they say we kind of a more, I mean, a direct argument, but I'm not going to that, right? So, but if you want to see how one can go, with the direct argument, please drop it in the comment, and I'll be happy to provide, I mean, the approach, to share it with you or discuss it with you if you want. Okay, so let's go into the proof. So what we are going to do is that we construct a map, and then so consider, let me explain what do we do. So consider the map, let's call it T, right? Defined from H into the dual space, right? Define as follow. So T maps F to TF, right, which is a linear bounded operator on H. So this means it's again defined from H into R, right? We are working on the field R. So for any U here, you have this dual pairing TF, U, right, which is nothing else. So this is exactly maybe define it to be this scalar product, of f and u. So maybe I don't put it in color, because color it looks like maybe we define this dual pairing to be, I'm just writing here, with this dual pairing being nothing else than the scalar product between f and u, right? For every f, I mean for every u. So let me just leave it like this. Now, what will be our goal? Well, so what we are going to do is that we are going to show that TH, right, which is obviously a subset of the dual space, right? We are going to show that this is dense in the dual space, right? But this is actually closed. The T of H is actually closed. So this will mean that T of H, right, is exactly H star, which means that for every phi in H star, right, there exists, I mean, we can prove uniqueness probably later, a unique f in H such that phi is exactly T of F, right? So this means saying that phi is exactly T of F means that, I mean, they agree point-wise, right? So this will mean that phi of U, right, will be exactly this dual pairing. But this dual pairing, we define it to be a scalar product of F and U. And then, I mean, it will be done. So this is the main idea of the proof. So I think we don't even have to go again into the proof, but because I said almost everything. So, but let's do it. So let me just erase this thing here. Then, okay. So so we define our map T. I mean, our map T is defined to be I mean, to be like this. So now this you can check. It is clear that You can check it if you want. It's actually easy to check, right? It's clear that the operator norm of TF, right, is exactly the norm of F, right? So this means T is the linear isometry from H onto TH, right? Which is let me put it in color, a closed subspace of H star. Okay, now as I said, in order to conclude, it is enough. It suffices to show that the image space, T of H, is dense in H star, right? So just recall. So this means we want to show that T of H, closure of this, right, which will be again T of H because this is closed, right? I have to show that this equals to H star. Now, well, for that, we use our trick that, from now on, if you are following this channel, you should be aware of this technique already to show that a set is actually dense in another space. So assume that H is an element of the bijoule, right? Which is H star star. So assume that you have H, right, which is an element of the bijoule, such that H restricted to TH, right, is equal to 0, right? This vanishes identically on TH. Now our goal, let me just write it, put it. Our goal is to show that H is the 0 of the bijoule. Okay, so this is what we want to show. By showing this, we will show that, by showing this, we are basically showing that T of H is actually dense into H star. Okay, now, since H is reflexive, right? It's a Hilbert space. And we saw that every Hilbert space is reflexive, right? Because every Hilbert space is uniformly convex, and by the minimum pitches theorem, we have reflexivity. So since H is reflexive, so this means the bijoule can be identified with H, or is isometrically isomorphic to H, right? So H can be seen as an element of H, small h, because remember we have H as an element of the bijoule, but the bijoule is isometrically isomorphic to H, right? Because H is reflexive, so we can see H as an element of the Hilbert space H, right? So H is in H and satisfies TF this dual pairing, right, equals to 0. Of course, this holds for every F in H, right? Well, my wonder where this comes from, but this is just by our assumption that H vanishes identically on TH, right? So this is equal to 0. Okay, so it follows that F comma H, I think I should put it in bracket, right? This is by definition. This scalar product is exactly, this is by definition of our operator T. So it follows that this equals to 0 for every F in H, right? And thus, because remember a scalar product is a bilinear form, so this means that H is equal to 0. Hence, 0 of H, right, that you can see again as 0 of the by joule because H is reflexive. So hence, we can conclude that TH lies dense in H star. Hence, for every phi in H star, right, there exists a unique F in H such that TF equals phi, right? But this means, they are agree point wise, so this means this joule pairing is equal to this joule pairing, right? But remember, this was defined to be scalar product F and U, right? Of course, this holds for every U in H. And yeah, I think we have just here have also the norm of phi, the operator norm of phi, right? In H star is equal to the operator norm of TF in H star, and this is exactly because we can show this exactly the norm of F in H. So with this we are done. Okay, good. So we are done with the proof. So I think this approach is rather straightforward, right? So, but of course we have a direct argument also, but I think it involves, it's a bit, the proof is a bit constructive. Yeah. Okay, so let's have a couple of remarks. So remark. So the above theorem, the Riesz-Fréchet Representation Theorem. So let me just highlight this. Actually assert that there is, probably I put it in color, assert that there is canonical isometry from H onto H star. So it is therefore kind of, I would say, legitimate, right, to identify H and its joule space. Let me write it here. It is therefore legitimate to identify H and H star, right? Because we saw that if you give me any linear bounded operator on H, right, I can find a unique representant in H. So it's actually, as I said, legitimate to identify the Hilbert space H and its Joule space. And again, remember in the introduction, I said that Hilbert spaces are actually, very important, play a crucial role in quantum mechanics, signal processing, and optimization. So let's have a look at some typical situations that commonly, used in that occur in optimal control with PDEs. So we put it like typical situation. Looks ugly. So typical situation. Okay, so let me just precise. This is commonly used in optimal control. With partial differential equation. Oops. Okay, so assume that H is a Hilbert space. Right, with a scalar product, right? Of course, with a scalar product that we denote again by the bracket, right? Then we put H here to emphasize that this is the scalar product on H, and the corresponding norm now assume that you have V, right? Oops. Assume that you have a linear subspace that is dense in H, right? Assume that V is a linear subspace that is dense in H. And just highlight V needs to be a linear subspace, and then we also need denseness. So we are writing in H. Now, furthermore, assume that V has its own norm, right? That we denote by just put a V down, and that V endo with that norm. Oops. V endo with that norm is a Banach space. So let me just now, and again, assume that, I mean, that the canonical embedding is continuous, right? That V embed continuously into H. So this means, I think this is not well properly. Oops. Good. This is just to say that the injection of V into H, right, is continuous. Well, what does it mean? It means that the norm of small v, right, in H is less or equal than a constant C, right, times the norm of V in capital V, right, and this should be for every V in V. I mean, you can think of, well, you can think of H as being the space L2 of 0, 1 on omega. Omega is actually 0, 1. And then you can consider V to be the space of continuous function over the compact set 0, 1. Right? I mean, this is actually a typical example of a Hilbert space and a subset on V. I mean, we saw that V is actually dense into H. V is a linear subspace, and the injection is even, is continuous. So this would be a typical example. So now, under all those assumptions, there is a canonical map that we call T again, now defined from the dual space of H into the dual space of V. Right? I mean, this canonical map is simply there is a canonical map T that is simply the, let me put it in color, the restriction to V, right, of continuous linear functionals phi on H, right? So, I mean, this is just another way of saying that T is defined the following way, right? The dual pairing of T phi, right? Phi is an element of the dual space of H, right? Comma V. This is the dual pairing V star V, right? Because this is just a way to say that this element lies in this space, right? And the other element lies in this space V. So this dual pairing is exactly equals to the dual pairing of phi and V, right? This is in H star H, right? And this is, of course, for every V in capital V, right? But capital V is a subset of H. So this is well defined. Okay, so it is actually easy to check that. So it is easy. You can do that. It is easy to check that T has the following property. Let's call it the first property is that, let me use this color. The norm of T phi right? I mean the operator norm of this in V star is less or equal than C times the norm of phi in H star, right? This is of course for every phi in H star. And this C is even, let me just do something. This C here corresponds exactly to the C, to the constant, what is that? To this constant here that comes from the canonical, from the the continuous embedding. So this C and the C below coincide. So, okay. The second property is that T is injective. This is easy to check, right? And the last one is that the image of T, right, is, or the range of T is dense in V star, right? Provided that V is reflexive. So so identifying we saw that the Riesz-Fréchet Representation Theorem allows us to identify a Hilbert space with its Joule space. So identifying H star with H, right, and using capital T, right, as a canonical embedding from H star into V star, one usually write we call it relation 9, right? So one usually write V is actually contained into H, right? That we see again as H star, which is contained into V star. So and so we often write this, right, where all injections are continuous and dense, right? I mean, provided that V is reflexive. I mean, denseness follows from, I mean, occur if and only if V is reflexive. You know why I'm trying to squeeze this thing, although I can just shift this a bit. So all injections, just highlight those, are continuous and dense provided that V is reflexive. Well, I mean, if you're lost, I mean, when I say that all injections are continuous, I mean the injections of V into H is continuous, the injections of H star into V star is continuous, right? Because you saw it here, like this we characterize the continuous embedding of H star into V star, this one. Okay, so one says that when you have relation 9, right, one says that, so one says that H is actually, we call H the pivot space, right? And this even is called, this triple, the triple V H V star, right? This is even called, for those familiar with optimization with PDEs, this is called Gelfand Triple, right? Provided that the space H is separable. Okay, so now note that the Joule pairing, what you should note is that, note that the Joule pairing thing was noted by this Joule pairing V star V and this scalar product in H, right, coincide whenever both make sense, right? Whenever both make sense. So what I mean is that this Joule pairing of, say, F comma V, right, in V star V, this is exactly the scalar product of and V, of F and V, yeah, in H, for for every F in H star, right, that which you can identify as being an element of H, right, and also for every V in V. So this situation, the situation becomes even more delicate, right, if V turns out to be a Hilbert space with its own scalar product, right? So we could, of course, let me just write it. This situation becomes more delicate if V turns out, put it in color, turns out to be a Hilbert space. Right, with its own scalar product. Say, let's call it, as another scalar product by this, right, associated to the norm that we denote by this. Now, of course, we could identify, we could of course identify the Joule space of V and V. We could of course identify V star, right, with V, right, via the Riesz-Fréchet Representation Theorem, right? So with the help of this scalar product, right? However, I mean, if you do that, however, our relation 9, right, that was actually, let me recall it, relation 9 was V is a subset of, I mean, embed continuously into H, right, which we identify with H star, which embed continuously into V star, right? So this relation, I mean, becomes, will not make sense anymore, becomes absurd, right? And for the simple reason that, I mean, if you identify this, I mean, you identify this with V. So this means, I mean, becomes absurd because then you will have that, I mean, V equals H somehow, right? Because you have V included into H, which is also included into V, and this will not make sense anymore, right? This will not make sense anymore. So so this means, I mean, this shows that, let me put it in color, one cannot identify let me write it, simultaneously V and H, right, with the Joule spaces. You cannot do both at the same times. So one has to make a choice. So the common habit is actually to, I mean, those familiar with optimal control with PDEs, the common habit is to identify H star with H, right, to write relation 9, and not to identify V star with V. So maybe I write it down. Probably not. So let me just write it. So the common habit, like what we usually do, is to identify H star with H, right, in order to write 9, relation 9 that we saw up, and not to identify V star with V. Okay, so now let's have a remark. So it is actually easy to, I mean, this is just for I mean, for the sake of your understanding. So it is easy to prove that, it is easy to I mean, to prove that Hilbert spaces are reflexive, right? It's easy to prove this without invoking the theory of uniformly convex spaces. Because this is what we did, right? When we wanted to show that a Hilbert space is reflexive, we basically proved that it was uniformly convex, and then invoke the Milman-Pettis theorem. So we can, you can show reflexivity without, without having to prove uniform convexity and invoke the Milman-Pettis theorem. Right? It's enough. So, well, how can you do that? So it's enough to, for you, it's enough for you to, maybe I put it in color to, probably this color. So it's enough for you to use twice the Riesz-Fréchet Representation Theorem. To use twice. This is theorem 5.5, right? The Riesz-Fréchet Representation. Probably I just cut it short and just say it is enough to use twice the Riesz-Fréchet isomorphism. Right? This is theorem 5.5, as I said, right? So we first do it, from H onto the dual space first, right? Write it properly, and then from the dual space onto the bidual. So it's enough to do this. So you don't need to prove uniform convexity and think of and invoke the Milman-Pettis theorem. It's okay. So let's have a final remark. Okay, in a Hilbert space, right? In a Hilbert space, in a Hilbert space H, right? Every closed subset, say M, right? Has a complement. Well, complement in the sense, let me tell you in which sense, because when you think of complement, you think of complement in the usual sense, but this is not the case here. Every closed subset M has a complement in the sense that there exists a subset L of H, right? Such that L is closed, right? The intersection of L and M is the singleton 0, right? This is the 0 of H, right? And L plus M is exactly H. So this doesn't look nice. I think this is better. Probably not. No. Well, this is a nice way to waste time. Okay, so if you're in a Hilbert space and then you have a closed subset M, then that subset M has a complement in the sense that you can find a subset of another subset of the Hilbert space H such that that subset is closed. It intersects M at the unique point 0, right? And the sum of the two subsets is the space H. Well, this is just kind of short proof, right? You can put L to be the orthogonal of M, right? If you remember, we defined the orthogonal of M as being, this is a subset of the dual space of H, right? But again, by the Riesz-Fréchet Representation Theorem, we identify H star with H So this means we can write, we just write L, that is M orthogonal as being this set of points U in H, right, such that the scalar product of U and V is equal to 0, right, for every V in M. I mean, the usual definition of the orthogonal of M, right, we require you to, I mean, when M is actually a subset of H, so this will be, require you to put a star here, right, take U in the Joule space. But as I said, we identify the Joule space with H, so we don't need to do so. So M orthogonal is obviously closed, right? And this you can prove, I mean, by writing M orthogonal as being the, I mean, arbitrary intersection of closed subset. So clearly, I'm not going to prove that. I'm just clearly this intersected with M is the empty set, right? I mean, not the empty set. I mean, the singleton 0, right? M orthogonal is closed, right? As I said, you can write M orthogonal as arbitrary intersection of closed set, right? And because M is closed, you can write H as being equal to M plus M orthogonal, right? Why is this? Because let me just write it. Indeed, for every F that you take in H, right, that F can be written as, I mean, the orthogonal projection M is closed, so this will be the orthogonal projection of F into M, right, plus F minus this, right? Now you can, I mean, this is just an element of M, right? And this, you can check, this is an element of the orthogonal of M, right? So this means that in F minus PF, and this is exactly, just drag it a bit. So this is exactly the projection of onto M orthogonal of F. Okay, I think we will stop here for today. So yeah, we will stop here. So thank you for joining. Thank you for joining. Thank you for actually joining me on this educational journey, right, through the Joule space of a Hilbert space. Just like in the classroom, mathematics is a collaborative adventure. So keep learning, keep teaching, and keep exploring. Until next time, this is Math Explore Infinity signing off.